Welcome again, Bichas, to the same lesson, because this is the second part of tangent vectors. If you are following Carroll's book, you may find that I use a different convention for writing the inverse of transformations. So I just wanted to clarify this real quick, that is that when I do the inverse of a transformation, let's say a rotation, which you have probably seen the videos, I just switch the indices up and down. But Carroll, he uses another convention. My convention is from Weinberg's book, so you can also check it out. But I really encourage you and I highly recommend you to read both books and see the conventions that they use, okay? So here's the video. I want to do one final analogy, which is that if we live in one-dimensional space, what's the tangent space at point P? It's just the tangent line to the curve. This is basic calculus. And you can span this whole space, this tangent space, with one vector. So for a one-dimensional space, you only need one vector as a basis for the tangent space. For two dimensions, which are the examples that we've been doing previously, I want to do the same thing. So let me draw here a curved grid. Okay, so you see that this space is clearly curved. We can pick this point P, and we are going to draw the tangent plane. Do you see that near the point P, this is a very good approximation? It's the same concept as in calculus for the tangent line. If you have here, for example, at this point, and you draw the tangent line, near the point, it's a very good approximation. It represents well the curve. And also here, near the point P, it's also very similar to the original curve. And well, the tangent plane is simply the same thing but done in two dimensions. If you have done multivariable calculus or vector calculus, you may have seen this in your theory. And for the two-dimensional space, again, we only need two basis vectors to span all the tangent space. So you may think that the tangent space is simply doing a linear approximation to the point where you are. Because when you establish a flat grid of a flat space, you are just doing that. You are doing a linear approximation. Because you can't work with vectors if you are not in a flat space. So you need to define always this tangent space, no matter the dimensions that you have. And this is basically doing a linear approximation. So when we are comparing vectors, we recall the example of the sphere that you may compare them like this if you move them across this line of if you move them to the North Pole, they were completely perpendicular. You can see that if you are very close to the point P, you can actually move vectors as if you were in flat space because it's not going to change that much. So this is an important concept. And now we're going to start working with vectors. So the tangent space is a vector space. So if we have some vectors v and w that are in the tangent space at point P, they satisfy the rules for vectors, which are that they are linear, they can be multiplied by real numbers and everything. We're going to work in n dimensions so that we are keeping all in the most general way possible. And in an n-dimensional space, as we saw previously with the 1D and the 2D case, if our space has n dimensions, our tangent space at every point is going to have also n dimensions. So we are going to expand, we are going to construct a basis at point P, for example. We have the first two, and we're going to have up to the nth basis vector. So we can write any vector which is in the tangent space at the point P. We can write this. V belongs to the tangent space at P. This vector is going to be written as v1 e hat 1 plus v2 e hat 2 plus dot 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 vn e hat n. And we can use index notation to write this more compactly, which is going to be this. Now we are going to use Greek indices for a general case where we are working in more than 3 dimensions or less. Greek indices are used for an n-dimensional space. So, for example, in chapter 2, we are going to be in general relativity. No, I'm sorry, in special relativity, and we are going to work in 4 dimensions, which are 3 of space and 1 of time. So the Greek indices are going to denote the 4 dimensions, which are all the dimensions of the space-time, and we are going to use lighting indices ijk only for spatial components. So we are going to switch to Greek indices. Now, remember from the last parts of the lesson that we were working with rotations. Okay, we have the rotation and the inverse. These rotations, we found them by defining the vectors as geometrical objects that don't depend on the coordinates that we choose. We can do the same, and we are going to write more general transformations that may satisfy these n-dimensional vectors, and we are going to denote them with lambda mu nu and the inverse lambda mu nu in this other way. So the transformations are going to be exactly the same. Everything is the same as in the past parts of the lesson. So I'm going to do the example. So the coordinates in a prime system will be simply lambda mu nu v nu. We transform the components which are contravariant, so we use the direct transformation. And now the basis is covariant, it's not contravariant, so we are going to use the inverse transformation. You see, it's exactly the same. So now we are going to write v prime as v prime mu e hat prime mu, which is simply lambda mu nu. I'm using this into this and also this here. So we are writing the definitions. Here we have lambda mu. Be careful, because if you write here nu and also here nu, this is illegal in index notation. You can't do this, okay? Because you are going to get confused with the news, because these news are connected together and these are also connected together. But if you go away from your sheet of paper and you come back later, you may think, wait, the mu's are connected in this way or in this way, or how? So you don't have to repeat dummy indices, okay? I think I said this in previous lessons, but it's always good to remember ourselves. When you have a double pair, well, when you have more pairs of dummy indices, you have to change the letters. Okay, so we are going to write here sigma, for example. Now this is v nu e hat sigma, and we have lambda mu sigma and lambda mu nu. From the video of rotations applied to vectors, the equivalent of this will be simply the Kronecker delta. This simply states that the matrix lambda with its inverse is identity. If you want to see why, well, you can go back to the parts of rotations of this lesson, and everything is explained the same with the r's, and we have simply renamed the r's into the lambdas. So it's everything the same as before. It's completely the same. So now that we have the delta, we are going to write v new e hat sigma and delta sigma new, and this is going to become e hat new because the delta, we are going to remind ourselves, the delta kills the repeat index and it places in the other one. So we are going to finish with v prime equals v new e hat new, which is v. So you see that the vector stays the same, and this is true because we have defined these transformations such that the vector doesn't change under any change of coordinates. It's the same as with rotations. I just wanted to include this in the video because we are then going to work with tensors and Greek indices and everything. So I wanted to do like the swap of mentality to a higher dimensional space here in this video. But everything that we have done here is exactly the same as the videos in rotations of the rotation of vectors. Okay, so if you have any doubt regarding the topics that we have been covering in this video, feel free to write in the comments, and see you in the next lesson.